All right, let's take a look at checkpoint 13. So this first question here, so we're given is we're told about this, experiment, this cycling event that is, whose results are going to fit a normal distribution. So because of that, we can make a lot of assumptions, we can make a lot of assumptions about the way this thing behaves or the way the data behaves. So um, I don't think this showed up in any of the videos, but I'm going to show you a really useful tool here to kind of do this analysis. So let me just start from scratch. So Desmos is one way to do this. I know that there are also ways, like for those of you who have TI graphing calculators, you might have to find some YouTube tutorials to show you how to do this, but I know they do normal distributions in a very easy way. Um, so yeah, I know there's tutorials out there to show you how to do that, but I'm going to show you how to do this in Desmos. So if you go to Desmos, why don't I just go completely from scratch? So let me move these over, reload Desmos, open the graphing calculator. If you open up this keyboard, functions, scroll down to, I think one of these headings is distributions. You want normal dist. You can also just type in normal dist and this will come up. So I want a normal distribution. And basically this right here this is a function that takes two inputs, basically two arguments. The first argument is the mean, and the second one is the standard deviation. So what's my mean? It's 62.3. So 62.3. My standard deviation is 8.4. All right. So this is what my normal distribution looks like. And I also want to find cumulative probability. This is the thing that's really powerful and going to help me really answer this question quickly. So first, find the probability that a randomly chosen cyclist had a time of less than 74 minutes. Okay, so the maximum time that I care about is 74. What's my minimum time? I don't have one. I'm looking for any time that's less than that. So in this case, the probability that my so the probability that I fall inside that window, can I draw? Draw is 0.918. So yeah, very quick with Desmos. So I mean, this is on Desmos, so you'll have access to this on the next exam. You can also use your TI calculator or whatever calculator you have. But yeah, make sure that you have access to this. Next, find the probability that four randomly chosen cyclists all have times between 50 and 74 minutes. Okay, so Desmos is not going to get us all the way here, but we need it to get us part of the way here. So now let's find the probability that a single cyclist finishes the race in this time frame. So minimum time 50 minutes, maximum time 74 minutes. The probability, so let's write this down. So for part B, the probability that a cyclist, why do I feel like I didn't record? Because I'm paranoid. Start recording. Okay. Back to this. All right. So the probability that 50 is less than or equal to X, which is less than or equal to 74, that's equal to 0.8466. But I want the probability that four randomly chosen cyclists all have that time. So what's my probability? It's going to be this number raised to the power of four. So I'll let Desmos do that for me. It's 0.8466 raised to the power of four. And I get 0.514 approximately. There you go. C, the top 5% of athletes qualify for Bike Fest. What is the maximum time that an athlete can take to complete the race to still qualify? Okay, so this is something maybe you'll find that I'm wrong on this, but I don't know that Desmos goes the opposite way on this. So I'm going to go ahead and kind of hunt. I'm looking for the top 5% of athletes. So basically, I'm not going to have a minimum time. So clear that out. So if you just delete what's there, it goes to a negative infinity by default, which is what I want. But I want to find a maximum time. And basically what I'm looking for is I'm looking for the probability of 5% or 0.05. So let's think about standard deviations for a second. In the videos, you've probably seen that when you get two standard deviations away from the mean, so let me rephrase that. So starting at the mean, within two standard deviations of the mean, that's about 95% of your data. So here's what I'm going to do. I'm going to do this 62.3 minus 2 times 8.4. And this is just to kind of give me I'm guessing. Let's try 45.5. 45.5. Okay, so that's not too far off. This is a little bit low. This is 2.27%. So basically, I'm being too strict. Let's go 47 minutes. Still a little bit too strict. 48, 49. Looks like we had it bookended. So 48 and a half. So now we're just like fine tuning this. And now it's just a matter of, we'll call that good. So, again, like all we can really do is kind of, I mean, you might find a better way, but as long as I'm looking at Desmos, this is the best method that I know about. And as always, this is the time when Edge decides it's going to lag on me. So I'll stall for time, but basically we were looking for that 5%, that 0.05, and it looks like that maximum time we found is 48. We'll just say 48.5 minutes. So as long as you finish the race under this time, you qualify for Bike Fest. So moving on to question 2. I'll go ahead and maximize this. I don't know if I need Desmos again, but I'll leave it open. We have 4 red socks and 8 black socks in a drawer. We take 2 of them out at random. A, find the probability the socks taken are of different colors. Okay, so what's that going to look like? So the probability they're taken of different colors. So how many ways can that happen? So I think one way it can happen is red, then black. That's one way it can happen, right? Let's find the probability that that happens. So what's the probability that I take a red sock first? I think that is going to be 4 of 12. All right, so assuming I do that first, then what's the probability I take a black sock? It's 8, not out of 12, but 11. So all told, this comes out to be 32 out of 132. Is that right? 1, 2, 2. Okay, good. Also, could be black then red. What's the probability I draw a black sock? That is 8 out of 12. And then I draw a red sock. That'll be 4 out of 11. So I think this is going to give me the same result. So 32 out of 132. These are disjoint, mutually exclusive outcomes. So I can add these together. That'll give me 64 out of 132. Does this reduce at all? I think these are both multiples of 4. So 16 over, what was that, just half? No, it's not. Okay, got a calculator, just do it. 16 out of 33. So it's not half, it's very, very close. All right, there we go. All right, so that's the probability that if I take out two socks, they'll be of different colors. Not quite half. All right, so B, now I have a random variable, capital X, stands for the number of red socks I take. Draw the probability distribution table for X. Okay, so what's the possibility? So let's talk about this. What are the possible values that capital X can be? I'm going to draw two socks. Is it possible I take no red socks? That's possible. Is it possible I take one? Sure. Is it possible that I take two? Also, yes. I think those are the possibilities. So let's take these. What's the probability that X equals 0? Or capital X equals 0. So basically what I have to do here is draw black then black, right? What's the probability I draw a black sock? That's going to be 8/12. And then another black sock is going to be 7 out of 11. So this is going to be 56 out of 132. And if I reduce, that's going to be 14 out of 33. All right. What's the probability that I draw exactly one red sock? Hopefully you noticed as you are working through this that part A did this part for you. So drawing exactly one red sock is basically is the case where you're drawing two different color socks. So this probability is part A. This is 16/33. And then what's the probability that I draw two red socks? That is going to be 4 out of 12 times 3 out of 11, which is 12 out of 132, which is 3 out of 33, which I know reduces, but I'm going to keep them all the same denominator because one thing I always like to do when I'm doing a probability check or a probability distribution is I want to make sure that the sum of all my individual components adds up to 1. So I have 14 plus 16 plus 3. That's 33 out of 33. So this is a good probability distribution. So now that I've done that, I can probably reduce. I'm gonna go ahead and avoid it. So let's draw the probability distribution now. So what's the probability that X equals X? And what is X? 0. It's actually, I'm realizing how strange it is to have these rows reversed. 0, 1, 2. Also, while I'm doing this, I suspect that many of you are going to be more comfortable dealing with the decimals. That's totally fine. Okay, here's my probability distribution. Part C, find the expected value of X. So expected value, basically, if I were to do this experiment, expected value is kind of a misnomer because very often the expected value is a value that I can't possibly get. And we saw that, you probably saw that a lot in the videos where the expected value is probably not going to be 0, 1, or 2. It should be something in between, like it obviously can't be 3. That would be impossible, but it's going to be something between 0 and 2. But it might not be one of those integers. So probably a better, more accurate way to think about the expected value of X is basically an average, a mean of all the possible values of X if you were to do this experiment a great number of times. And a good way to think about this is basically it's a sum of like these weighted averages. So if we add these together, so 0 times 14/33 plus 1 times 16/33 plus 2 times 3/33. I get what? I get 16 plus 6. That's 22/33. That's exactly 2/3. So this is what I mean with like the expected value. Expected value is 2/3. Obviously, I can't draw 2/3 of a sock without some kind of alteration. But this is the expected value if I were to do this experiment. All right, moving on to part 3. The company I work for produces the caps that go on water bottles. These caps are produced via automation and required to have a diameter of 1 inch with a tolerance of 0.01 inches in order to be usable. The machine that produces caps that have a the machine that is used produces caps that have a mean diameter of 0.999 inches with a standard deviation of 0.005. This sounds like this is tailor-made for this Desmos function. So we're using a normal distribution. So the mean is 0.999. Standard deviation is 0.005. Okay, so we have a couple different steps to go through here. So here's my standard deviation. So now that we've plugged that in, what do we have to do with it? So these caps are produced, okay. They're required to have a diameter of 1 inch with a tolerance of 0.01 inches. So I am looking basically for the probability that I will be between 1 minus 0.01 and 1 plus 0.01. So 0.99 and 1.01. So my probability, so let's write this down first before we go any further. The probability that 0.99 will be less than or equal to x, which will be less than or equal to 1.01 is, let's take it down to like 6 places, 0.95016. That's the probability that, basically any one cap that comes off this process will be usable. So now what am I doing with this? If I produce 100,000 caps per day, how many will be usable? So now I can use this probability and multiply it by 100,000. So 5 zeros, 1, 2, 3, 4, 5. I can basically round to the nearest whole number there. The number of caps that I would expect to be usable are 95,017. And that comes directly from our normal distribution. All right, that is all for checkpoint number 7. Or 7, what am I talking about? Checkpoint number 13.